back in this advanced conduction series, and today we will continue with our lectures on advanced conduction heat transfer. And just let me make a brief recall of the previous lecture. That is, what we did was we talked about the continuum hypothesis, that is when we can analyze any matter like this as a continuous matter, right, as a continuum. And I also talked about the mechanisms of the conduction heat transfer in solids, liquids and gases, right. So in this lecture what we will do is, firstly, so in one sentence we will derive the thermal energy balance equation. But why we need to do that? So to answer this question, let me put in front of you another question. Okay, so just let me put today's heading, that is lecture 2, right? This is the lecture 2, and the question that I would like to put is, that is, if you are a mechanical engineering student who has already gone through the basic heat transfer course, then you must have seen this formula, right? So this is what? This is the Fourier's law in one dimension for an isotropic material. Now I am sure that most of you will not be using this word isotropic material. So if anyone asks you in the interview that q dot equal to minus k a dt dx, obviously area should be there, k a dt dx. So what are the assumptions behind this equation? Then most of you will miss this word isotropic material. Okay, and I will tell you, and I will give you a mathematical proof that is why I am inserting this new word isotropic. Okay, so now my question is that I have here the heat flux, so not heat flux, the rate of heat transfer, and this is the temperature gradient, and this Fourier's law is making a connection between these two, right? So my question is that why do we need this Fourier's law, or in other words, why do we need this connection between the rate of heat transfer and the temperature gradient? Okay, so now before answering this question, let us suppose that you are an engineer, a thermal engineer, or maybe you are a material scientist. Okay, and you are supposed to select a material for the engine design of an aircraft or maybe of a car. So then what should be your steps? So you have to select a material. So then you have to know that what is the maximum stress that can be induced in that material. Now stresses can be induced because of the loadings, the external loadings, right? Other than that, there can be thermal stresses. So we all have solved a problem in strength of material like this, that is, we have a bar fixed between two support, and if the temperature of the bar is increased at a up to a particular value, then what will be the thermal stress induced. So that is why we need to know that where is the thermal stress induced, and throughout the whole material, throughout the whole engine body maybe, where is the maximum amount of thermal stress. To know that, we need to know the temperature profile, and to know the temperature profile you need to solve the governing equation for temperature, either analytically or by a suitable numerical method, and which comes under the area of computational fluid dynamics. Okay, so in this course the numerical methods are not in the scope, but I will try to show you some comparison between the numerical methods and the computation and the analytical method for a same problem. And obviously the analytical solution is the actual solution within that assumptions. Okay, now these are the main drawbacks of the analytical methods. That is, you don't have analytical solution for each and every each and every situation you face in the practical reality. Okay, so now let us proceed for the thermal energy balance. So actually the answer is, in the thermal energy balance we will see that this heat flux is there, and if this heat flux is there but we need a governing equation for temperature, then we need something correlating this heat flux with temperature, and that is what is doing that is what is the Fourier's law is doing. Okay, that is, it is correlating the heat flux and the temperature because we need that temperature profile. Okay, and in the thermal energy balance we will see now that the heat flux will come, and we need to write this heat flux in terms of the temperature. Okay, now most of you have already, maybe you have already done this derivation of the thermal energy balance, right? And if I am not wrong, then you have taken a small elemental volume like this, right? Where, or not even a volume, you have taken just a small elemental strip like this, and this is maybe dx, and this is at a distance x, whatever. And if you see this, and maybe you have taken this cross section area as A, and you have derived it by this method, that some heat is going in qx, that is at a distance x, and it is qx plus dx, that is leaving this control volume. Okay, and then you have balanced this energy. Okay, so this is actually a very good method, a very basic and good method, but in this course I will try to put a new flavor in all the chapters. Okay, so I will do this thing also. Okay, but now I will start by some another pathway to derive the thermal energy balance. Okay, so that you can get a new flavor. Okay, so let me start. So I will start the derivation of thermal energy balance. Okay, equation. So quickly tell me that which law of thermodynamics will give the energy balance equation. Just pause the video for a moment and quickly type in the comment box. So the answer is the first law of thermodynamics. Right? And now, can you write the equation for the first law of thermodynamics for a closed system? Can you write that? So for a closed system, so I hope that you already know that what do we mean by a closed system. Okay, so just for the sake of completeness, closed system means what? Mass is permitted or not? So mass is not permitted, right? Mass is not permitted. And heat is permitted or not? Heat is also not permitted, right? So heat is also not permitted. Is that correct? No, heat is actually permitted. Okay, so these basic questions or this basic concept, that what do we mean by a closed system and what do we mean by a open system and what do we mean by an isolated system, and what are the corresponding terms in fluid mechanics. Okay, because the analysis for an isolated system or the analysis for an open system and a closed system, they are totally different. So you must need to identify that if the system is closed, obviously this name, this closed system name is not important, but the uh, but the concept is more important. Obviously the name is also important, because as an engineer you must know that what is a closed system, because if you don't know the correct terminologies, then you cannot communicate with other engineers. Okay, so heat is permitted. Okay, heat is permitted, or in a more general sense, energy is permitted. Okay, so in my IISc interview, I was given I was given a simple problem. So when I was solving that problem, one of the panelists, he asked me that if the system is open or closed. I said closed. Then he asked me that heat transfer is zero or not for a closed system. So in any good institute, they will always start from the basic, if you know the basics or not, because uh, so I started that question without drawing a control volume, because I was habituated in that manner that I don't need to draw the control volume, because I know that there is a, I mean, I have already drawn the control volume in my head. But you should start, I mean, at least in your head and or in your mind, you should start by drawing a control volume from the very basic. They don't care that how much formula do you know, they only care that how much basics do you know. Okay, how much clear are your basic concepts, because each and every formula can be derived from the basic concepts, and that is what we will do now. Okay, so for a closed system, uh, the form of energy, I mean the form of first law of thermodynamics is delta E is equal to delta Q minus delta W, right? Is it right? Okay, this is also not right, because this is not delta E, it is dE. And why? This energy is a property, so it is a point function and not a path function. So energy is an exact differential, but heat and work are the path functions and not the point functions. That is why they are inexact differentials, right? Now another question comes that uh, when we can write this work also as exact differentials. So this is your homework, that when in which case I can write this work as an exact differential. Okay, you just type that in the comment box. Okay, so the statement of the first law for a closed system is dE is equal to del Q minus del W, where this is what, this is the total energy, right? This is the total heat interaction. Okay, and this is the total work. Okay, now here another question comes. If I write del E is equal to del Q plus del W, and also if I write not del E, dE is equal to minus del Q plus del W. So out of these three equations, is 1, 2 and 3, which one is correct? Just pause the video for a moment and think, and then you type in the comment box. Okay, so actually the answer is, you should say that my question is incomplete, because before asking this question I need to clear my sign convention. So in this equation, my sign convention is that work done by the system is positive, and heat going into the system is positive, right? If I follow this sign convention, then only my equation 1 is correct and 2 and 3 are not correct. Okay, now you have to tell me that what should be the sign conventions for the equations 2 and 3 to be correct. Okay, that is what should be the sign convention, so that I can tell my equation 2 and 3 are correct. So they both can have same sign conventions, or they both can have different sign convention, that you have to tell. So I will always give you these types of small conceptual questions, because these are very important to build a strong basic. Okay, now if you find these questions or these fundamentals difficult, then just type in the comment box. I will cover these things in a small video separately. Okay, so because as engineers we are acquainted with this form, this equation 1, so we will proceed through this equation 1, that is dE is equal to del Q minus del W. Okay, so now this E is what? Total energy, right? Total energy, and that is equal to thermal energy, okay, plus mechanical energy. Okay, so here this thermal energy is nothing but the internal energy. Okay, and if you if you are analyzing for a fluid, that is a flowing fluid, then it will be the enthalpy, that is the total heat content, that will be the thermal energy of that amount of fluid. Okay, but here we are considering a solid, and the solid is not flowing. Even if the solid is moving, it is moving as a whole, it does not have anything like flowing. Okay, actually this thing that whether you will be considering the enthalpy or internal energy, that depends on if the system is flowing or not. Okay, this PV H, what is enthalpy? H is equal to U plus PV. Okay, so this PV is nothing but the flow work. Okay, so if the system is flowing, then it must have the flow work term. Okay, and this is the mechanical energy, that is the kinetic energy plus the potential energy. So internal energy is what? Internal energy is energy of the atoms or molecules with which the material is made of. Okay, so they actually possess some vibrational and translational or rotational energies. So, and other than that, it can also include the chemical energies, the magnetic energy, etc. Okay, so this is the internal energy, and so this is the microscopic concept. Okay, and this mechanical energy is like the half mv square and mgh that you already know from your basic concepts of mechanics. Okay, so here we have to go for the governing equation for temperature. Okay, so mechanical energy has nothing to do with temperature. Okay, so thermal energy we will be talking about this one. Okay, that is the thermal energy. Now let us see this term. This is work, this is thermodynamic work, right? Now if you like, you can type in the comment box that what do we mean by the thermodynamic work? I need an exact and precise definition. Okay, so if you want, then you can write that. So now, if there is a solid, then you cannot apply a displacement work. Okay, and even if the solid is deformable, we are neglecting that deformation work. Okay, here, and also you cannot have any shaft work in a solid. You only can have an electrical work transfer uh, by, I mean, how you can have. So if I have a solid like this, right, if I have a solid like this, then if you insert some wire inside this solid, not around the solid, if you insert some wire, maybe you open up this and you insert some wire like this, okay, and then you put this off. Now you flow some current through that wire, and there will be some joule heating. So now if I say that this is my control volume, this outer surface of the solid is my control surface, and the volume bounded by this outer surface of this solid, it is my control volume, then my wire is cutting this control volume. That means some electrical work is being transferred through this control volume. Okay, then only you can say that I can transfer some electrical work. Okay, now this is a same question, I mean a very popular interview question. Okay, that is, if I have a solid like this and I put an wire inside. Okay, so let me draw the situation, it is very interesting. Okay, so if I am having a solid like this, why it is not converting to a rectangle. Okay, let me draw a flash. Okay, if I am having a solid like this, solid, liquid or gas, anything, maybe a gas, okay, maybe a gas, and I am having a wire inside this, and I am flowing a current I here. So there is joule heating. Now my question is that here the gas will heat up. So is it work transfer or heat transfer? Okay, is it work transfer or heat transfer? Okay, so this is a very good and interesting question. All of you must answer this question in the comment box. Okay, and if anyone answers the, I mean I will comment on the answers. If the answers are correct, then you can see that which of the answers are correct, and if none of you is able to, I mean if no one can give the correct answer, then I will prepare a separate video explaining this thing, that is, if it is a work transfer or if it is a heat transfer. Okay, so let me box this question, I will not erase it. This is a very good question. Okay, okay, so this is a separate question. Okay, so I am not considering this mechanical energy here, right? So I am not considering this kinetic energy as well as mechanical energy. Here I am not considering this. These are not zero, but I am not considering this. Okay, and if these are zero, then only this E is equal to internal energy. Okay, so for the time being, you can also consider that yes, I am analyzing a solid that is in a static condition. Okay, and this thermodynamic work, this also we are neglecting here. Okay, if the wire is I mean if the wire is wound around this solid, then the effect of that heat generation we will take care that thing inside this del q term, that is the heat transfer term. Okay. So our first law boils down to what? du is equal to del q. Okay. And if you consider a finite system, then I can write that is du dt is equal to q dot, that is the rate of heat transfer is equal to change in the internal energy. Okay, neglecting any work transfer. Okay, so now let us quantify mathematically this part, that is the heat transfer. So the q dot, now this q dot will have two parts. Okay, one is qs, q dot s, another is q dot g. So q dot s is what? Q dot s is the surface heat transfer. That is how much heat is penetrating through the surface of this material. Okay, so this is a surface phenomena, right? This is a surface phenomenon, and this is what? This is the heat generation. Okay, heat generation rate, heat generation rate, and this is also actually the rate term. Okay, so let me complete it. That is, this is a volumetric phenomena. That is, this qs is only happening in the surface, this qg is happening all over the volume. And what I was talking about is this is actually the rate of surface heat transfer. Okay, because it is dot, q dot s. Okay, so q dot s means dqs by dt, not by. This is a incorrect incorrect terminology, that is dqs dt. Okay, so now let us dive down into this qs dot and this qg dot one by one. Let us see that how can we quantify these things. So this is qs dot. Okay, so to quantify this, let me define something called heat flux at a point on a surface. Okay, heat flux at a point on a surface. So let me have a coordinate system first. So this is my coordinate system, x, y, z, and there is the origin. Okay, now I will have a surface like this. Okay, now let me have a area delta A, or A, only A. Okay, and the centroid of the area is here, and the position vector is this one. Okay, that is r. So if q is the, okay, so q is the or Q dot average. This is the average heat transfer rate through this area A. And why I am talking this, I mean why I am telling this average thing, okay. So that is because this area A is containing infinite number of points, okay, but through all those points the heat transfer may be different. So if I have to define a single heat transfer rate through this area, then I have to go for the average of all the heat transfer through all the points on that area, okay. So that is the Q dot average. So my, okay, another thing is that this is the direction of unit normal of the area A, okay. If this is the case, then my heat flux Q double dot through this area A, okay, is defined as Q dot average by A, okay, Q dot average by A. Now let me give some name to this point, that is the centroid of this area A, as P. So heat flux through this point P, okay. So let me term this as Q double dash average. So heat flux, so this is equal to heat flux through point P. So now you just tell me that mathematically how you can get this point P. Just think for a moment and type in the comment box. Now the answer is, that is Q double dash is equal to limit A tends to 0 Q dot average by A. Now there are two catches. One is this limit A tends to 0, this cannot be taken in any manner. You have to ensure that at any instant this A should contain, okay, this A should contain the point P. Then only if you put A tends to 0, you will get the point P. Another catch is I already have told that no matter is continuous. If you go to the molecular dimension, then you will see that there are finite gaps between the molecules. So if you are putting A tends to 0, then maybe you have gone to a dimension in which you are seeing the separate molecules. So after you have taken the limit, maybe your domain is now this, okay. So if your domain is now this, then you can see that you have 3, 3, 6 to 8 molecules in your domain, and you cannot consider this domain as a continuum anymore, because at any point the properties will vary, and also not at every point the properties are defined, because not at every point the molecule is existing, okay. So at this instant, at this position there are no molecules, right. So you cannot go to A tends to 0, then your continuum hypothesis will not be valid, okay. So for the continuum hypothesis to be valid, you cannot apply A tends to 0, you cannot do that. Then what should we do? The actual thing will be A tends to A star. Now what is this A star? So A star is the minimum area for which continuum hypothesis, I am writing in short, is valid. Okay, this is the A star. So the definition is, I am writing the final statement and the definition. So heat flux passing through passing through point P having position vector r, okay, on a plane, okay, having unit normal, okay, so let me write this with another color, having unit normal in hat, okay, at a time t is equal to q double dash. So q double dash is a function of this position vector r. It is defined at a time t. It is also dependent on which surface you are considering, through which the heat flux is passing. So this is not only the case for heat flux, for any flux. It can be the electrical flux, it can be magnetic flux. For everything it will be dependent on the surface. Okay, so this is defined by limit A tends to A star, right, Q average by A. Okay, so now, and why it is a function of n, let me give you a basic visualization. So if I am having a point P here and I am having two surfaces, one is like this, another is like this, okay. So through this point P, this blue surface is having its unit normal like this, okay. So it is maybe n hat 2, and through this point P, the red surface is having its unit normal maybe like this, okay. So n1. So q double dash defined at point P is not same for the red surface and for the blue surface, okay. Okay, so now let me introduce another concept, that is the concept of heat flux vector, okay. So heat flux vector is denoted by q arrow, just like any other vector, okay. And again I will need this diagram actually, okay. So let me let me copy this diagram. Let me paste it here, okay. So now I don't need this q average thing, thickness, let me reduce. Okay, now stroke. Okay, so now heat flux vector, this is not dependent on area. Okay, so this is not dependent on the choice of area. So clearly this is a function of only the position vector at the time t, that is at which point you are considering the heat flux vector and at which time, right. So this is defined as q double dash, that is a function of rt and ex, or let me write not ex, let me write I cap. So basically I cap is the unit vector toward x, and so I cap is equivalent to ex cap, or ex, only ex, or e1 actually. Okay, e1. J cap is equivalent to uh, writing this e2, and k cap is equivalent to writing e3. Okay, these are the unit vectors. Okay, these are just the notations, and to write this as vectors, let me write hat. Okay, and this into e1 cap plus q double dash r, okay, e2 cap plus q double dash r e3 cap. Okay, so this is a vector, this one is a vector, and this is the x component of that vector, this is the y component of that vector, and this is the z component of that vector. Okay, now you see, that means this vector, heat flux vector and heat flux at a point, they are related. Okay, so now if on this surface, now if this is an elemental surface dA, okay, around this point P, so what will be the heat flux through this point P? That will be given by this one. I mean, this will be collinear through this n cap, and this is q double dash and a function of r, t and n cap. Okay, let me use some different color here. Okay, so let me use this blue color. Okay, so the heat flux, it is collinear to the n. Okay, collinear to this n, this is heat flux, and it is a function of r comma t comma n cap, right. And now my heat flux vector, it does not have anything to do with this dA, so it can be oriented in any direction. So let me choose any other color, maybe maybe which one, this one. Okay, okay, this one. So it is like red, so let me choose another. The visual effects are very important, right. It will directly go into your mind. So let me use this purple. Okay, so maybe this is my heat flux vector at a point that is situated at a position vector of r and at a time t, right. So if the angle between them is cos theta, is theta, then my q sorry, you can see from here only, that is my q q double prime is equal to mod of q bar into cos theta, right? So that will be q double prime at r comma t comma n cap is equal to mod of q bar, that is a function of r comma t into cos theta, right? Now what is this? This is nothing but q bar dot n cap, right? So I can say that this is component, right, component of heat flux vector in the direction given by n cap. Okay. So this this relation, let me write it once more, that is q double dash, that is a function of rtn, is equal to q, that is heat flux vector dot n cap. Okay, this is a very important correlation. So now I will again need the coordinate axis here. So let me just take this one. Let me copy this and paste it here. And I don't need now this surface. Now I will define, okay, I will need this one. Now I will define, I will need this one, but for this my system. Okay, so this is my system and the volume is V cut. It is the volume, the total volume of the system, and total surface area is A. Okay, not the total surface area, this surface is denoted by A. Okay, now if I take an elemental surface area like this, okay, and now I say that this is the position vector of this point at a time t, that is r. Okay, then my heat flux passing through this point, okay, heat flux passing through this point is this. Okay, so this is not converting into a straight line. So first let me draw the unit normal. So this is the unit normal. Okay, and my heat flux passing through this area is this one in the same direction, that is q double dot, that is a function of r, t and n bar. Okay, and this elemental area has the magnitude of dA. Okay, so now I have to define the sign convention for this also. Okay, so my heat going into the system is positive. This is my sign convention. Okay, so this is my sign convention. Okay, if this is the case, now you see that if I am having this q bar, okay, so let me draw this dA here. So this part, this dA, I am drawing it again. Okay, maybe here only. So this part I will be drawing with which color? maybe with, I should draw it with yellow, the zoomed version. Okay. Okay, so this is the zoomed version of this surface. This is the dA. Okay, this is dA. So now if my heat flux is going out of the surface, okay, so this is the unit normal n cap. Okay, this thing. Now if my heat flux is going out of the surface like this, okay, that is the heat flux. So then it should be negative. And if my heat flux is going inside the surface, let me draw it with another color, maybe this one is blue. Then it is positive. So for this case I will have the negative heat flux, and for this case I will have a positive heat flux, right? So now when will I will be, I mean, in now this is the thing that I have drawn for the case of heat flux. Now if I want to represent the same situation in terms of the heat flux vector, then what will be the situation when my heat will be going out of the surface? So for that let me draw it here only. Okay, so this is my surface and this is again dA. Okay, so this is the unit normal, again this is the unit normal n cap. Okay, so if my heat flux vector here is like this, draw it with blue. So this is my heat flux vector. So if my heat flux vector is in this situation, so you see the angle between the heat flux vector and this unit normal is less than 90, and my heat flux vector is going out from the surface. Now if I am doing this one, that is I am rotating my heat flux vector in a clockwise manner. Now at this situation my heat flux vector is tangent to the surface. So the dot product with this normal n cap, that is 0. So no heat flux is passing through this surface dA. Now if my heat flux vector is like this, then my angle between the normal and the heat flux vector is more than 90, then my dot product is negative. So again if my heat flux vector is this, then my dot product with the heat flux vector with that of the normal is positive. In this case that is 0, in this case the dot product if is negative, right? Okay, so that means now you see that in this case when the dot product is positive, then that means my heat flux vector is negative. So when the dot product is positive, that means my heat flux is leaving from the surface. So I am again repeating, this is a very important concept. Okay, I mean if you do not understand this, you will have the confusion regarding this sign convention throughout your life. Okay, so if my heat flux vector is like this, then my heat flux is leaving from the surface. In other words, if my dot product of the heat flux vector and the unit normal n is positive, then my heat flux is leaving the surface. If it is 0, then it is neither leaving nor entering, it is not passing through the surface. If it is negative, if the dot product of the heat flux vector and the unit normal is negative, then it is entering through the surface. Okay, Okay, so now I am just drawing it like this. So this is my heat flux vector, right? Now, so I have screamed for so many times now that if, okay, so I need to reduce the thickness. So if Q dot N is positive, then what? Heat flux leaving. Okay, then heat flux is leaving. But according to my sign convention, so this is my sign convention, right? If the heat is leaving from the system, that must be negative. That is why I will take here my heat flux as, okay, I will take here my heat flux as minus Q dot N. So now are you clear about this significance of this minus? And in another case, if I take, that is my Q dot N is negative, then my heat flux is leaving. I mean this is, I mean these two things are true, that I have shown already, okay, by rotating this vector, okay. But according to our sign convention, if the heat flux is leaving, then my Q double prime, that must be negative. Sorry, this is entering, I am extremely sorry, this is entering, okay. So if my heat flux is entering, that must be positive, but my Q dot N, that is negative. So to make it positive, I have to incorporate an extra minus sign. So this is the actual correlation that we will follow here, okay. So therefore, at this elemental area dA, my heat flux is Q dot Q double prime, that is a function of R T comma N, that is equal to minus Q dot N, okay. So my total heat transfer, total surface heat transfer, that is the Qs, that will be integral of Q dot into dA. So Q dot into dA is what? Q dot into dA is the heat transfer from, through that surface element dA. So if I have to get the total heat transfer rate, then I have to integrate over the surface. So it is integrated over the area A surface. Now I can write this Q dot as minus, sorry, I can write this Q double prime as minus Q dot N dA, right? Okay, obviously A should be here. Now, have you heard about the Gauss divergence theorem? You must have heard in your engineering mathematics course during your studying in B.Tech, right? So if I apply that, then it will be a volume integral, and it will be minus divergence of this vector Q dV. It will be converted to a volume integral after the application of Gauss divergence theorem G dt. Okay. So Gauss divergence theorem is applicable on both a scalar quantity and a vector quantity. Okay. So for the scalar quantity, it will be the gradient of the scalar into dV, and obviously integral over that. And for a vector quantity like this, it has to be a divergence. Okay. So my Qs finally, I'm just concluding, Qs is minus gradient of, not gradient, divergence of Q into dV, volume integral. Okay, so this is the QS. Now I will be concluding this lecture. Before that, I will give you some homeworks. Okay, the first is uh, what will be our next step? Can you guess? That is going for this Q generation, right? Q generation. Now, this Q generation, as I have told, it is a volumetric phenomena. So here we will define something called small q triple prime. Okay, and that is the volumetric heat generation rate. Okay, and it has the unit of watt per meter cube, SI unit. So Q double prime has the unit of what? You must say now. You must be able to say this. This is watt per meter square. And just now see the thing that why it is denoted as Q double prime. So these two prime signs are denoting nothing but the power on this m meter square. So here it is meter cube, that is why it is Q triple prime. Okay. Okay, so you have to tell me that this Q triple prime is a function of which quantities. Okay, so firstly Q triple prime is a function of which quantities. Now if you know this, now Q triple prime is volumetric heat generation, that means it is the heat generation rate per unit volume. Okay, if you know this, that Q triple prime is what? Heat generation rate per unit volume. So get an expression of Q dot G in terms of as a function of Q triple prime, and that is very easy. It is, the answer is uh, lying in the definition of this Q triple prime, right? So you must be able to do this, right? So before the commencement of the next class, you just get yourself cleared with all the questions, the small ones, the basic questions, like that interview question also, that is a very good one, is one. You get yourself cleared with all these questions and you put in the comments that if you have any doubt regarding anything, not only regarding this lecture, not only regarding advanced conduction, but regarding anything. Anything mean that must be under my purview. Okay, otherwise I will not be able to solve your problem. So you just post anything that is if you want to say that my teaching is a bit fast, or if it is a bit slow, then also you can tell me. I will modify according to the comments. Okay, so we will continue in the next lecture from this Q dot G, and we will derive the final form of the thermal energy balance. Okay, so until that, bye bye, take care.